Great, thanks very much. So the point of this talk is to look back at the work that we've done on the RISC-V LLVM backend so far, and hopefully talk a little bit about lessons learned, the approach that was taken, and hopefully give some insight that might be useful for other people looking to work on similar projects, or perhaps wider development efforts within the LLVM community. This is actually the sort of second LLVM backend project I've done, so it builds on top of the previous work I did when I was a researcher at Computer Lab at the University of Cambridge. We had a research backend, a research architecture with its own custom instruction set, which is where I kind of got started with compiler development. So this effort itself very much built on the lessons I learned there, particularly in terms of the challenges of working downstream and things of that nature. This work has been done primarily at Low Risk, which is the sort of not-for-profit open source hardware focused organization, which I co-founded around 5 years ago now. Great. So the structure of this talk is that I'm going to give a little bit of an introduction to backends in general and RISC-V, because I'm very aware that people in the LLVM community have a fairly different background in terms of exposure to backend work versus middle-end, front-end, and the like. I'll give an overview of the current status, the approach that was taken, and most importantly, talk through sort of how we got there and the journey that we took, and end with some of the sort of lessons learned and observations. And in general, I'll sort of try and keep it relatively high level, but if you have particular questions, then dive in at the end, because there's a sort of version of this talk I could give, which would be very, very interesting to the small number of people who work on backends day in, day out, but I'll try and keep it so that it's fairly accessible to people who aren't but don't meet that description. Great, and so just to give a bit of a basic introduction to RISC-V, it's an open, extensible ISA. It started at UC Berkeley. I think their official start date is sometime around 2010, but it was only around 2014, end of 2014, about the same time Low Risk started, that it was becoming, they were starting to talk about it more publicly and started putting on events and that sort of thing. There are several base ISAs, so the 32-bit RV32i and the 64-bit RV64i, both of which being fairly minimal instruction sets, so around a little bit under 50 instructions, which is sufficient to, if you wanted to, build a Linux kernel or major operating system. Though realistically, most people wanting to run Linux would, of course, implement various standard instruction set extensions. In the RISC-V world, these all have single letter names, and they're concatenated together to make a somewhat confusing ISA naming string, at least for people who aren't familiar with it. And so you typically say on a standard Linux-capable machine, you'd have the M extension for multiplication, A for atomics, F and D for single and double precision floating point, and then C for the compressed instruction set extension, which of course will also be useful on most microcontroller designs. The standard RISC-V ISA encoding has each instruction as, or the base encoding has each instruction as 32 bits. The compressed instruction extension adds a variant of instructions in 16 bits, and these can be freely intermingled in your instruction stream. Now, with all of those options for ISA combinations, there are, of course, an array of different ABIs, and we'll talk a little bit later about some of the challenges there. So you have essentially variants for soft float and single and double precision hard float, and of course for 32 versus 64-bit. The other base ISA I didn't mention was RV32E, which is just a variant of the standard ISA, but rather than having 32 general purpose registers, you just have 16, which is primarily for very resource constrained targets. Interesting features around, an interesting aspect of RISC-V, which of course, as you may have seen, ARM have recently picked up in their microcontroller line is the ability to add custom instruction set extensions. So the ability to, there are large portions of the opcode space which are free for vendors to implement their own instructions, their own custom extensions. There are various vendor-specific extensions in the wild at the moment, though none of them currently upstream in LLVM. So what does a LLVM backend entail? In terms of where to look, you want to go and take a peek in LLVM/lib/target. You'll then see a directory for each of the supported backends. The work to actually bring an LLVM backend up includes the MC layer, so essentially the assembler, disassembler, object file emission support, definitions of your instruction set, so the instruction encodings, the assembler, mnemonics, and that sort of thing, through table gen descriptions, the patterns for instruction selection, again through table gen, specifying selection DAG patterns, a whole bunch of target-specific hooks and miscellaneous C++ logic to get everything working together. Hooks either, because of course that there is a strong dependency on the shared target-independent code in the back end, and this is often the way that you handle that is by implementing some sort of specific functionality in the back end, either to further control something like the lowering process from LLVM IR through to the selection DAG and through to instruction selection, or sometimes to manipulate middle-end passes in a way that produces better code gen for the target. And of course, in terms of actual development activities, a large portion of the time ends up being spent on tweaking, bug hunting, bug fixing, and the like. So to give a little bit of background in terms of when the project started, there was an initial RISC-V LLVM backend port that a student at UC Berkeley had started. This was very heavily based on the upstream MIPS backend. It kind of worked for a number of simple examples, though ended up having problems for more complex inputs. The issue that we saw was that this wasn't a particularly good base for further development. We're also seeing that although there was substantial interest in RISC-V, a lot of the groups who were looking at using it and using it with LLVM were grabbing that as a starting point, making some downstream fixes to get the workload they're interested in running, and then that was the end of it. Those fixes would never make their way upstream. And indeed, in fairness, it's quite difficult to, it was quite difficult for people to make incremental improvements due to the nature of that work. So the approach we took was to build something upstream first, produce it incrementally. This affects both the review strategies, so trying to ensure that things can be split up as cleanly as possible, so ensure that reviewers aren't reviewing some huge 5,000 line patch to add the whole backend in one go. Also partly testing, although generally LLVM has a very strong testing culture. We tried particularly hard to ensure that each incremental change had tests that matched it wherever possible. We attempted to split the instruction definitions, so the machine code layer, the assembler mnemonics and encoding versus code gen patterns. In most backends, those are intermingled. I took the explicit decision to try and have instruction definitions which match the ISA manual as closely as possible, so it's easily to sort of cross-reference and check that everything makes sense, and then having code gen patterns at the end of the file. This mostly worked, though it has some issues around, but I might get back to later. And I guess related to that, we also worked to build the target from the MC layer up, rather than, although there's a lot of bang for your buck in terms of getting code gen running relatively early, everything was built on top of a fully functional tested MC layer. So getting the assembler working before then adding patterns for code gen. And in general, for most of the lifetime of the target, the focus has been getting functionality working rather than spending lots of time on micro-optimizing beyond the obvious improvements for generated generated code size and performance. As the backend's matured, we're now spending a much higher proportion of our time looking at performance and code size. And so the current status of the backend became a default backend as of the 9.0 release. We've sort of hit all the major targets in terms of supporting the most common, well, essentially all of the standard RISC-V instruction set extensions, those which have been ratified. So the RV32 IMA FDC, and the same for 64-bit. All of the APIs, soft float and hard float, other than RLP32E. And we spent quite a lot of time testing it with a variety of workloads, spec, the GCC torture suite, the Linux kernel, which compiles and runs with some caveats. As you know, there's a long-running story with building Linux kernel with Clang, and more meaningfully, a very large corpus of Linux user space software. So thousands of build root packages will build and run out of the box with few problems, and the ones which don't, as far as we can see, mostly come down to build system issues due to a dependence on GCC. And this is something I'm sort of hugely proud of, to be honest. It's been a very enjoyable, rewarding process, and there's lots of great stuff to come. So just to give a few statistics, we can argue about their meaningfulness. To get a little bit of insight, there are around almost 400 commits which touch libtarget RISC-V. Obviously, some portion of those will be fixing up interfaces and other fairly straightforward things, as well as some much more bulky commits, which obviously take much longer to produce. In terms of lines of code, it's actually relatively small. So just counting actual source lines of code, under 9,000 lines within libtarget RISC-V, around 4 to 4.5 thousand lines in table gen files, so that's including spaces, white space and comments. And in terms of tests, well, in test code gen RISC-V, there's around 160 files, a huge variety in terms of the number of tests within each file, but we've built up a fairly reasonable corpus of targeted unit tests there. Now I'm going to spend a little bit of time talking about how we got there and go into a bit more detail about the approach taken. This talk focuses on the technical aspect of this work. I should note there was a fairly substantial non-technical component going on in parallel. It kind of coincided with kind of spinning up work at low risk full time, growing it from 0 people to 1 people, and now 10 people, and going on in the background. So that was a fairly big piece of this work in terms of ensuring that it could be supported and funded through our not-for-profit, but I'll be focusing primarily on the technical aspects. Now, hopefully that's somewhat legible. I spent a little bit of time working back and trying to pick out some key events in terms of when things landed in the code base. The selection of major events is somewhat arbitrary. There's some meaningful things which don't quite fit on here. The initial work started around the end of 2016, where the first few commits were landed. It wasn't until sometime around the middle of 2017 that I started working close to full time on it, rather than a little bit of time in evenings and weekends. So we had the sort of initial MC layer patches landed sometime around Q1, Q2 2017, and then a huge chunk of work landed around the end of 2017. So the complete, relatively complete machine code layer support, relatively complete initial pass at CodeGen for the base instruction set architectures, enough to compile, and a large portion of the GCC torture suite and have it execute correctly. 2018 was when we started seeing sort of broader contribution from started getting other people on board, contributing things like support for instruction compression. There's a fairly chunky piece of work on Atomic's CodeGen. There's quite a lot of subtleties there. And then around the beginning of this year was when we started knocking off most of the challenges for 64-bit Linux support. So where most people want to compile with hardflow APIs, with PIG and TLS and those sorts of things. And then, of course, more recently, RISC-V becoming a default backend. So this gives a brief overview of the way that we structured the patches. You can sort of look through the commit history for a more detailed rundown of how this worked. One thing I wanted to highlight here was that, so initially, the very first couple of patches are relatively trivial, adding the triple parsing, basic elf defines, and the like, that you can write simple tests for this. We couldn't see a good way to split it. So the next 5 to 7 patches, it wasn't really possible to add tests for each piece. We considered sort of merging everything into one big patch, getting it up to the point where you could assemble something, generate assembly output, but that also seemed kind of unpleasant, didn't seem particularly nice, given that there were meaningful sort of partial milestones whereby you could demonstrate that the back-end code was partially implemented in compiling. Particularly initially, there's quite a bit of back and forth figuring out just which hooks you need to implement, what classes need to be implemented in order to get the back-end to compile. But from that bolded line, from the point where we got the first assembly tests, each patch from that point can include tests which demonstrate that the added code actually works as intended. So that is roughly the first set of patches to add MC layer support. The next chunk of work was adding basic code gen. I kind of listed up to this point, adding proper calling convention lowering, because from that point onwards, I'd say both the MC layer and code gen were functionally complete, and then the sort of options in terms of where to go, with regards to whether you're implementing further performance optimizations or adding support for new other instruction set extensions, it's much more parallelizable and you have sort of more options there. We're able to split it up in a fairly sensible way. Started off implementing just a few basic ALU operations, materializing constants, so you get basic trivial IR inputs working, fleshed that out with memory operations, conditional branches. The slightly ugly thing about this was that in those early stages, there's the the function prologue and epilogue insertion isn't yet implemented. The ABI isn't yet compliant with the RISC-V spec, so it's not actually executable, but you can demonstrate that the expected assembly instructions are being selected. So in terms of, I'll maybe return to a few of these if there's any time at the end, but I thought it would be useful to list a few things which were particularly interesting or fiddly or maybe different to other architectures. So RISC-V is, as the name suggests, it's designed to be a completely vanilla RISC architecture. So from that perspective, it may seem surprising that there's anything that requires any real work in LLVM at all. Shouldn't it just all be straightforward? As it turned out, there are a few things that required somewhat more thought and effort. The compressed instruction set support, linker relaxation. There's a whole piece of work around atomics lowering, which is challenging in LLVM in general. So ensuring that the for regions in a load reserved and store conditional sequence are protected, so that you maintain compliance with the specifications requirement for forward progress, required a reasonable amount of work. And just generally speaking, the number of extensions and options and ABIs is fairly, there's a fairly aggressive, there's a pretty large number of combinations to explore there, even compared to other mature backends, things like MIPS, which is itself cycled through many ABIs in its lifetime. And of course, a key part of getting it to the point at which we got it to was due to help from the wider community. This is a almost certainly very incomplete list of people who have contributed, either in terms of patches or code review, comments on RFC threads and the like. Particular shout out to Luis Marques and Sam Elliott, who work with me on the low-risk compiler team. And of course, it's been particularly pleasing as the backend's matured, as we've had a growing number of external, wider contributors, and also contributors adding large new features, such as most of the LLD work done by other people, the instruction compression support, and other pieces of work which are currently in review, such as the machine outliner. What was particularly useful for us was, in terms of coordinating work, was arranging weekly calls, just a very informal sync-up for people who are actually working on the back end. What are you currently looking at this week? What's blocking you? We've kept this very lightweight. It kind of worked better than I thought it would, actually, in terms of just surfacing questions which, even before going through a detailed code review, or surfacing areas where people were looking at the same thing at the same time to try and deduplicate effort. And of course, another aspect of this was also sharing RFCs, which I'll touch on in a moment. We put a reasonable amount of time in terms of outreach, both to try and ensure that, to kind of spread the word for the work that was going on in the RISC-V backend, and more generally to try and get people involved in LLVM. I ran a tutorial and coding lab last year at the LLVM Dev Meeting, and various talks at other LLVM events, RISC-V workshops, and other smaller events, which hopefully has helped to bring people on board to the RISC-V backend, or otherwise get them involved in LLVM. As you can imagine, a large portion of time has been spent on testing. I realize there's nothing at all insightful in saying that testing and documentation is important, but it doesn't mean that it's not true. It's exactly as you'd expect. I don't think we've ever regretted investing more effort into increasing test coverage, or otherwise making it easy to run a large corpus of tests. The GCC Torture Suite has been particularly useful for us in bringing up the backend. I know it was very useful for WebAssembly and various other backends too. We also put a reasonable amount of effort in terms of testing a large corpus of programs with Buildroot, Linux kernel, real-world assembly, and the GCC Torture execution tests, thanks to Sam Elliott's work, are now added to the LLVM test suite, runnable with lit and buildable with the CMake build system on whatever architecture you choose. You may have to add a target-specific blacklist. I think currently in Tree there's just x86 and RISC-V, but I'd encourage you to have a look and try and get that up and running for whichever target you work on. So we found our experience with reviews and RFCs has been hugely positive. One thing that I've found interesting speaking to people working in other communities is that it's not always obvious to them that RFCs are about much more than just getting permission to do something. I've found it particularly valuable getting insight from a wider community on alternative implementation approaches, or aspects which I hadn't yet thought about. Reviews have been discussed multiple times at LLVM dev meetings and the like. It remains challenging ensuring that there's sufficient bandwidth to get patches reviewed. I found it somewhat challenging in the early days of the LLVM backend, though ultimately I'm very grateful for everybody who helped get things through. We found with the low-risk team, we spent now a pretty large portion of our time reviewing other people's patches, which is great in terms of keeping things moving, though obviously we need to ensure that the load remains well spread out reasonably well, so that we can keep sort of meeting our implementation targets. A few challenges to highlight. So one of those is, and I'll be somewhat selective here. I think ABI lowering in the front end it's a barrier for the number of, given the number of projects looking to target LLVM IR. So I'm not sure if you're aware that Clang will actually, there's a huge amount of ABI lowering that goes on in Clang. It will actually count for registers which it expects to be used. This is essential to produce code which is compliant with the RISC-V ABIs. So in the integer ABI, for values which are passed in registers, they are sign or zero. Well, integers passed in registers, they're sign or zero extended depending on the sign of a C type. They're any extended if they're passed in memory. So Clang has to actually go and figure out, whether it be passed in memory or registers, in order to introduce those attributes. And and there are similar restrictions for a floating point ABI. I know it's been discussed several times in the past, but producing some sort of shared library, or more ambitiously, encoding more of the C type system in LLVM IR in order to allow for greater code sharing between different front ends would be hugely helpful here. In terms of what I might do differently, I suppose in terms of the approach, partially due to interest from one of our sponsors, and partially due to the fact that it seemed a simple way to start. A lot of the initial focus was on 32-bit support. I think we may have got more external users earlier if we put more time into 64-bit Linux support, but that has pros and cons in terms of attracting, getting more people kicking the tires. And another final thought is around greater code sharing between backends. I think there's probably much less bang for your buck to be gained here versus working on things like the ABI lowering, because there aren't that many people starting off new backends. Though it is worth pointing out that copying and pasting between backends is pretty rife. For instance, if you go and grep in libtarget for in flag, you'll find that there are a whole bunch of backends copying the concept of a flag. Now, in selection DAG, you have what's currently called a glue and chain. So the chain is specifying the ordering. The glue specifies that two instructions should be scheduled together. It was renamed from flag to glue back in 2010, yet you'll find most backends copy and paste the same code from the same source that still uses his old naming, which is not really referred to anywhere else in LLVM. And I think I'm out of time, so with that, I will go to questions. Thank you.
Let's thank the speaker again. We have time for questions.
Yeah, Sean Landon. What is the status on the bit manipulation instructions? And is there any plans to try to make those LLVM intrinsics, any of those?
Yeah, so the Embercosm folks who've been working on the bit manip, I think, have either a poster or a talk, so they're probably the best people to talk about that. So there are patches which are in review, which add some basic support. I guess it's actually one of the challenges I list here for RISC-V in general, which is, how do we handle extensions which are not yet ratified? So how do we handle the idea of a extension which could then change during the development process, which is probably something we'd want to think about for bitmanip if we're going to merge it upstream before it actually gets finalized.
Hi, Thomas Lively. I work on the WebAssembly backend. We're about to sort of create and implement a second C ABI for WebAssembly that will depend on a bunch of extensions to the MVP spec, kind of like the RISC-V ISA extensions. So I was wondering if you had any insight onto how to manage ABI compatibility, or maybe when a single compilation unit is using multiple ABIs or trying to link together between different ABIs, how you manage that translation, if at all.
Yeah, so this is something where there's kind of work going on in the wider RISC-V community. So we do have L flags which you can set to indicate what ABI you are using. So that's checked at link time. That's basically as far as the story goes. GCC and binutils do implement additional flags which can specify ISA variants, which can also be useful, but we don't currently support that in LLVM. And I'm not sure there was a story there on supporting scoping that was smaller than a file, because a related issue is you might want to describe the ISA variant which a particular function implements, particularly if you have generating multiple versions of a function with different extensions. But yeah, checking a flag at link time is about as far as we have in the RISC-V world. We've got in the RISC-V world, I mean, for the RISC-V backend, I've implemented the ABI lowering in a function rather than trying to get the table gen infrastructure to work, as that was a much easier way to support the sort of parameterizable nature of the RISC-V ABIs.
I have a question about the splitting MC and cogen instruction definitions. So could you say a few words about the rationale behind that? And also, I understand that with the MC layer, you want it to be as close as the real instructions in the specification. So does that mean in the cogen instruction definitions, a little bit higher level or more virtualized or shorter? So, yeah.
Yeah, I think mostly making is shorter, and also if we're so say with the MC layer definitions, if you're ordering all of those and setting them out in a way that closely matches the ISA spec, that's not necessarily the most natural way to read the cogen patterns. So you can sort of handle the MC layer stuff, and then later organize all the cogen patterns in a way that makes logical sense, rather than trying to handle both at the same time.
Thanks for the presentation. Just a little question. You were talking about this entire space of opcodes that are available for vendors. What do you think the LLVM community's position should be if a vendor wanted to integrate some extensions in the LLVM backend?
Yeah, my feeling is that LLVM has always been very welcoming to code contributions. I think that should be that if there is if somebody is willing to support an addition to LLVM and it doesn't negatively impact other users, then I think LLVM should be welcoming to all those extensions. There's some development communities. It's a slightly controversial issue in the RISC-V world, because on the one hand we don't want to see splintering and a whole bunch of different custom extensions, but I figure if chips are out there, then I think it's much better if upstream LLVM could generate code for them, rather than encouraging or even requiring multiple downstream forks.
More questions? If not, let's thank the speaker again.
Thank you.